Good morning. This is Dr. Michael Olson from Meteorology 2010 at Daytona State College. This video is going to cover the first portion of Chapter 1 from Dr. Ahrens' Essentials of Meteorology textbook. Chapter 1, of course, covering the Earth's atmosphere. The first section, which will be covered in the video, just talks about the atmosphere's origin and formation. First of all, we go back to the beginning of the Earth, and we remember that as the Earth was first formed from elements in the newly formed solar system, they were just masses of molten rock. And so the Earth was pretty much nothing but one molten rock when the Earth was first formed, with all the heavier elements staying inside of the molten mass, and the lighter elements, such as hydrogen and helium, escaping towards the surface. So those lighter elements actually became the very first atmosphere of the Earth right after it was formed. Over time, as the Earth started to cool, there were pockets of hot air and hot gases inside of the Earth, which began to escape from inside of the Earth's crust. This is a process called outgassing, where the gases inside the Earth are released outside of the crust. Many of these chemicals that were released include carbon dioxide and water and many other chemicals as well, but those were two of the primary ones. So as the Earth cooled, more of these gases were released, and pretty soon the hydrogen and helium atmosphere started to be replaced by a carbon dioxide and water atmosphere. As the water concentrations continued to build up, some of that water began to fall into mountains and forming lakes and oceans, and pretty soon there was a large amount of water all around the entire Earth, to the point where it is today, where the Earth is about 70% water. Well, there's something else about the water that is very special, and that is that water easily absorbs carbon dioxide. In fact, one of the greatest ways that the Earth naturally removes carbon dioxide from the atmosphere is through bodies of water. Classic example of where we see this is actually soda, soft drinks. And what makes it carbonated? It's just carbonated water or carbon dioxide dissolved in water. It's a natural process that goes through the entire Earth. Great way of removing carbon dioxide from the atmosphere. There was another element that was outgassed into the atmosphere, nitrogen, N2. That nitrogen, when it came out into the atmosphere, it stayed. Nitrogen is a very, very stable element. It very, very rarely reacts with anything. So pretty much whatever nitrogen was released into the atmosphere stayed there. So today, the majority of our atmosphere is actually not oxygen, but nitrogen. With the abundance of carbon dioxide, water, and nitrogen in the atmosphere, that helped to allow the plants to evolve and start to produce oxygen about 100 million years ago. And over the last 100 million years, the balance between water, carbon dioxide, nitrogen, hydrogen, helium, and all the other gases kept evolving and changing to the point where we have our current atmosphere today. This table from your textbook actually shows the current structure of our atmosphere. You can see the most abundant compound is actually nitrogen. The atmosphere is 78% nitrogen and only about 21% oxygen. And then other elements, argon, neon, helium, hydrogen, xenon, so on, are much, much smaller amounts, but they are still present in our atmosphere. On the right side of the table, you see other gases that are more variable, where the numbers change from time to time. For instance, carbon dioxide, the amount of carbon dioxide in the air varies a lot with season. Higher amounts of carbon dioxide when it's in summer and lower amounts of carbon dioxide in winter. So you have carbon dioxide, methane, nitrous oxide, and ozone, as well as other particles and aerosols in the atmosphere. I skipped water vapor on purpose because there's something very important about water vapor which comes later on in the course. This is probably one of the most important compounds in the atmosphere because it's what determines weather. Water vapor varies more than any other compound in the atmosphere. You can have completely dry air where nearly 0% of the atmosphere is made of water, or an extremely humid atmosphere, such as we have here in Florida, where nearly 4% of the atmosphere is made of water vapor. And that variability is a key role in what causes weather to actually form around the Earth, different types of weather. Now, what causes these numbers on the right side of the table to fluctuate? Well, that depends on what we call sources and sinks. A source is considered anything that produces some of that compound into the atmosphere. For instance, in this figure, we're looking at carbon dioxide. As water evaporates, carbon dioxide does too, so that is a source. When soil decays and plants decay, that releases carbon dioxide. Animal life through respiration releases carbon dioxide. Burning plants, volcanic activity, fuel combustion, those are all sources of carbon dioxide. And then a sink is considered something that removes that compound from the atmosphere. For instance, dissolving carbon dioxide into water removes carbon dioxide from the air, so it is a sink. Photosynthesis, plants draw carbon dioxide from the atmosphere, as well as marine life, so all of those are carbon dioxide sinks. Now, when we consider all the sources and the sinks together, it is nice. Usually we have a perfect balance so that the amount of whatever chemical we're talking about, in this case carbon dioxide, it doesn't change much. So if the sources match the sinks, the amount of that chemical remains pretty constant. If they're misbalanced, however, then the numbers will change. One of the biggest concerns we have with a misbalance between sources and sinks is carbon dioxide. This graph shows carbon dioxide concentrations measured from Mauna Loa, Hawaii, where we have a good station that accurately measures the amount of carbon dioxide in the atmosphere. And you can see this zigzag line, and basically every time that it zigs up, that's going into the summer of a year. Every time it zigs down, you're going into winter time, because in the winter, the sinks are a little bit stronger than the sources, but in the summer, the sources outweigh the sinks. That's a yearly cycle, but this graph shows something a little more startling, and that's that the average yearly amount is actually increasing. And this is not new. This has been a huge debate for many, many, many years when discussing climate change. The biggest concern is that we have too many sources of carbon dioxide and not enough sinks. So the amount of carbon dioxide is increasing. Now, someone can say, well, look at this, it's just 40 years. How do we know what happened before that? Well, we have ways of measuring that, one of the main being ice core samples from Greenland and Antarctica and other areas of the world. That gives us pretty good information. Now, I do need to point out this is still only for the last 1,000 years, as we'll see in the last segment of the course when we talk about climate change. This is a very small sample compared to the entire history of the Earth. This is not the first time that carbon dioxide levels have increased this drastically. Um, and it won't be the last either. But it is a very accurate and startling description of what happens when sources outweigh the sinks of a compound. There are other chemicals, such as ozone, which can cause a lot of problems. Ozone is kind of unique. Ozone is one where, in some cases, it's a good chemical, other cases, it's bad. For instance, ozone is absolutely important in protecting us from high energy radiation from the sun. So it protects us from getting sunburns and skin cancer, at least with limited sunlight. Of course, if we're out too much, there's only so much the ozone can do, and we'll still get sunburns. But if it weren't for ozone, we wouldn't be able to exist out on the surface. The high energy radiation would be too much. Also, the smell of rain. That's one that people don't know very much. But when you go outside after a thunderstorm and the you have a nice sweet scent in the air, that's actually ozone. And in small concentrations, it's not harmful. It's a nice sweet smell. It's a way for the air to actually clean itself out. So it's quite natural and good. However, if concentrations get high enough, then ozone can start reacting with other chemicals in the atmosphere, such as nitrogen dioxide or sulfur dioxide and other stuff. And when it does, it produces a heavy, thick, dirty fog, which we call photochemical smog, and just sits over the city and is very, very, very harmful to human life. In this picture is of Mexico City during a really bad photochemical smog event. So, um, so we are very careful about what sources we have for ozone, as well as what sinks are available, so that we can make sure we have a good balance to try and prevent harmful harmful concentrations of ozone for human life. That finishes the first segment of Chapter 1 on the Earth's atmosphere. In the next video, we'll start looking at the atmosphere's structure, both what the pressure profile and temperature profile look like in the atmosphere. Should you have any questions about this video, please feel free to email me. I would be happy to answer any questions you have.